Okay, so today we're going to switch to a little bit new topic and we'll circle back and review some of the writing equations from Monday if we have time at the end here. Just a little note, I had warned you that units 4 and 5 we're going to go very quickly because we're short on time. Unit 4 test will be coming up on Monday. So that'll be May 1st. I'll get that sent out to everybody in the next day or two so everyone has a copy of it. They're ready to go. Since we are getting towards the end of the semester, I'll make sure I make a note on there if you guys want to start early before class on Monday, you can as well. Same as always, we'll take the class time Monday to work on the test. You can have more time if you need it, but the 45 minutes in class on Monday is the only class time we will take for it. Okay, so our next topic in our graphing and displaying data unit here is on variation. And variation is really just explaining how two or more variables interact with each other. There's really only two types of interactions that our variables can have. There's a direct interaction. So it's called direct variation. And in a direct variation, and I'm just going to refer to the variables as x and y for now. We'll fill in some more practical examples later where our variables are other values. But in a direct variation situation, if the value of x gets larger, the value of y also has to get larger. Not necessarily in the same amount, but in a related amount, a proportional amount. Or, if the value of x gets smaller, the value of y also gets smaller. Again, not the same amount, but again, in that related amount. And the other type of variation is inverse variation. An inverse variation, as you might guess, is the opposite. If the value of one variable gets larger, the value of the other variable has to get smaller. Again, and not necessarily the same amount, but that related amount. Or, if the value of the first variable gets smaller, the other variable gets larger. Again, in some sort of calculatable amount. And these are really the only two types of interactions. Some textbooks make it more complex by combining them in different combinations, but really it can all be broken down. If you're only focusing on two variables, they either interact directly or inversely. Now, if you get more than two variables, one of two things has to happen. Either one of those variables has to be assumed to be constant, and we'll look at a situation with that, like that with the ideal gas law later today, where we have to hold the temperature constant, so it's down to two variables. Or there could be multiple different types of interactions. It's not possible for three variables to all vary directly with each other. One of them has to be in an inverse relationship with one of the first two. For our purposes in this class, we're going to stick to only two variables being related, so we'll keep it down to these two simple relationships. Let's talk about direct variation. As we said, in direct variation, one variable gets larger, the other variable has to do the same thing, and again, in some sort of related proportional amount. The definition of direct variation is simply that the ratio y over x equals a constant. Because of this, direct variation is often referred to as a constant ratio. Because of that, one of the ways we can calculate with direct variation, if I'm looking at, y1, x1, y1 type of situation, is that the ratio of y1 to x1 has to equal the ratio of y2 to x2. So any of our proportions that we set up are actually illustrating a direct variation situation. Now, rather than using this setup, often it is more feasible, easier to use, more convenient to set it up like this. Y equals a constant times x. So if we know if x and y are directly related or very directly with each other, we know the equation, the relationship is going to take that form. For example, I might say that, pen out about it. If I know that y varies directly as x, all that is telling me is that I have the situation y equals a constant times x. So that's all it's doing, is saying we have that form of the equation. Now, of course, there can be more to it. This relationship itself is important to understand, to know how those quantities interact with each other. But then it's useful to have some sort of a known condition. And what all a known condition is a situation where we know the values of the two variables at the same time. So whether we have a situation we measure the two variables and see what they are, or whatever. And sometimes in science, it's often referred to as an initial condition. I used to work as an engineer, and a lot of times we didn't know the formula or couldn't remember the formula, and rather than looking it up, if you could remember that the relationship was direct or inverse, you could look at the things you've already produced, take measurements or whatever, and use those known values to then create the formula and go from there and save a lot of time. So let's say we're told that y varies directly with x again. And now we're told that when x is 8, y is 20. So now we have two pieces of information here. This first one here is exactly what we had up here, telling us it's a direct relationship, showing that y equals a constant times x. This next piece here is the new piece. This is that known condition. X is 8 when y is 20. And so what that allows us to do is to plug into this formula, replace y with 20 and x with 8. And now we can solve to find what the value of that constant is, what k is. So divide by 8 to solve that equation. 20 divided by 8 is 2.5. Here the 8's cancel out, so we know that our constant equals 2.5. So this allows us to further define our relationship. Knowing that they were directly related gave us this form of the equation, but now we know that that constant 8 equals 2.5. So we can put those together to define that relationship further as y equals 2.5 times x. So that's how we can construct a formula using the knowledge of this direct variation. And in most cases, there's a second value that we're trying to find from that. For example, once again, if I tell you that y varies directly as x. So the wording can all change there. Sometimes y varies directly as x, sometimes y varies directly with x. Sometimes they use the terminology y is proportional to x. All of them mean the same thing, that they take that form y equals kx. Get back here. So then when x is 9, y is 33. So there's that known condition. Now find y when x is 12. Now we're being asked then to extend it to a new situation. So we start out where we did before. Y varies directly as x is telling us y equals a constant times x. We have our initial condition, or known condition. X is 9 when Y is 33. So we're going to replace Y with 33 equals K. Replace X with 9. And once again, we're going to solve for K, that constant. So we're going to divide by 9. 33 divided by 9 is, what is that, 3 2/3? Equals K. So now that we know that the constant is 3 2/3, we can come back up here and further define this relationship. So rather than just knowing that Y equals a constant times X, we know that that constant is 3 2/3. So Y equals 3 2/3 times X. And then we have that final question. Apply it to that new situation. Find Y when X is 12. So Y equals 3 2/3 times 12. Well, 3 2/3 times 12 is, I believe, 44. So Y equals 44. I'm just going to double check that here. It is 44. Perfect. So why do we care? What purpose does it serve for us to have this direct variation? Well, there are a lot of things in science, engineering, and definitely in medicine that are directly related. Let's look at a dosage based on weight. In a dosage based on weight, the dosage is directly related to the patient's weight. Or, since we're using kilograms in most cases, you could say to the patient's mass if you prefer. So let's look at a situation here where we know a patient weighing 42 kilograms receives 21 milliliters per minute in an IV. Again, knowing that this medication is based on weight, how much should a patient weighing 68 kilograms receive? So we start off with the relationship. Dosage is directly related to the patient's weight. So the dosage equals a constant times the weight. Next, we have that known condition, known state. The weight of 42 kilograms is a dosage of 21 milliliters per minute. I'm going to leave the units out of here. I could put them in, but it just complicates things at this first stage. I'll come back and put them in a little bit. So D is 21, that's the dosage, equals K times the weight of 42. We divide by 42. 21 divided by 42 can either be 1/2 or 0.5. So our constant here is 0.5. So that tells us the relationship here is the dosage equals 0.5 times the weight. Now I should point out here that it is very important that we know what even though I left the units out, it's very important that we know what those units are and how they apply here. We know that the weight is in kilograms and the dosage is in milliliters per minute. If the weight were in pounds, it would change that constant, obviously, because it wouldn't be 42 kilograms anymore. So it's very important that we know what those units are, and if we go to apply this formula, that whatever unit was used for the dosage is used again, and whatever unit was used for the weight is also used again. So anyway, now we're asked, find the dosage for a patient weighing 68 kilograms. So D equals 0.5 times 68. Well, 0.5 times 68 is 34. And we know that the units before on the dosage were milliliters per minute, so they have to be milliliters per minute again. So that 64 kilogram patient should receive 34 milliliters per minute for their IV flow rate. So if we really wanted to, we could have left the units in here. So our dosage would have been 21 milliliters per minute equals K times 42 kilograms. And so when we divided out the 42 here, it would have been 42 kilograms we'd divide out. 21 divided by 42 is still 0.5. But now we got milliliters per minute divided by kilograms. That's milliliters per minute per kilogram is that unit. So if we use that as a unit on our constant, if we're saying that the dosage is equal to 0.5 milliliters per minute per kilogram times the weight, what this is implying to us that whatever goes in here for weight has to be in kilograms. That's the only weight or mass unit that's in that constant. And so if that goes in as kilograms, it'll cancel out the kilograms, leaving us with milliliters per minute, so we know that the dosage will be in milliliters per minute when we're all done. Another example is that light intensity on a surface. Assuming the distance stays constant. If I don't change the distance. Light intensity on a surface is directly related to the square root of the bulb wattage. So, start off with this here. Light intensity on the surface is directly related to the square root of the bulb wattage. So if we let I be the intensity, that's equal to a constant times, not W, but the square root of W, where we're going to let W be the bulb wattage. At a given distance, a 40-watt bulb gives a surface intensity of 8 lumens per square inch. Find the surface intensity if the bulb is switched to 100 watt. So I take out the bulb and replace it with a 100 watt bulb. So there's actually two things I have to do here. I have to start with this first piece. That's that known condition. So the intensity is 8 lumens per square inch. I'm just going to put in the 8 there. Equals a constant times the square root of 40. So solving this, dividing by the square root of 40 now, I know that my constant is equal to 8 divided by the square root of 40. It's not a very pretty constant, so let's calculate it out. I get 1 point, I'm going to go 4 decimal places, 1.2649 equals that constant. Now, they want me to find it for a new setting, apply it to a new situation. Find, if we know that the intensity is equal to 1.2649 times the wattage. Find the new intensity if the wattage is 100 times the square root of the wattage, I should have said, if that wattage is 100. So it's I equals 1.2649 times the square root of 100 now. So we got a few steps to calculate here, a couple steps at least. First of all, the square root of 100 is 10. And 10 times 1.2649 is 12.649. And that is going to be lumens per square inch again. So we went from 8 lumens to 12.649 lumens. More than doubling the wattage of the bulb only increased the light intensity at the surface by about half, by 50%. Well, let's switch over then to inverse variation. So inverse variation, as we mentioned before, is whatever one variable does, the other one has to do the opposite. So if we're looking at x and y, if x gets larger, y has to get smaller. Or if x gets smaller, y has to get larger. The relationship here is that x times y equals a constant. So these two variables are a constant product. Which means, rather than y2 over x2, or y1 over x1 equals that y2 over x2, it's x1 times y1 equals x2 times y2. Now that formula there might look really familiar from the last unit, and we will come back and show you an example of that before we're done here. A more common use of this formula, rather than saying x times y equals k, we tend to say that y equals a constant divided by x. So inverse variation is the constants divided by the other variable rather than multiplied by the other variable. So if we are told y varies inversely x, well, that's telling us is we have that form of the equation, y equals constant over x. Obviously, that's not very exciting, so let's look at it given that known condition. So we're told y varies inversely with x. And we know that when x is 8, y is 6. So again, we start off with this piece of information here. Y varies inversely with x, simply telling us that y equals a constant divided by x. Then we have that known condition, the given condition. So we're going to put 6 in for y equals k over, we'll put 8 in for x. And to solve for k, we're going to just multiply by 8. So 6 times 8 is 48. K equals 48. So once again, we can now further define that relationship. It's not just y equals a constant divided by x. We now know that constant is equal to 48. So y equals 48 divided by x. Now, one of the neat things about either type of variation is we can switch the x and y. In direct variation, if you switch the x and y, it changes the constant, but you'll still get the same result down the line. For inverse variation, we can switch the x and y, and it doesn't change the constant. If I had started out with x equals k over y, and put in 8 for x and 6 for y, I'm going to multiply by 6 to get k by itself. I'm still going to get 48 equals k. Again, that's because x times y is a constant product. K is x times y, not x divided by y or y divided by x. So it's going to be the same no matter what order we put the variables in. We might look at Y varies inversely with X. And being told that when X is 12, Y is 10. Find Y when X is 15. So again, we start off with that relationship. Y varies inversely with X. That's just telling us Y equals a constant divided by X. We have that known condition or initial condition. X is 12 and Y is 10. So I'll put 10 in for Y and 12 in for X. And we'll solve for K. Multiplying by 12 on both sides gives that 120 equals K. So our constant is 120. So we can refine our definition of the relationship here. Y equals 120 over X. And now find Y when X is 15. Put 15 in for X. 120 divided by 15 is 8. So Y is 8 when X is 15. So you can see here, X got bigger. It went from 12 up to 15. Y got smaller, went from 10 down to 8. Not by the same amount, but by that related amount again. Let's look at some examples of inverse relationship here. One that we kind of hinted at earlier is that change of concentration formula, or sometimes called the concentration adjustment formula. And that formula, of course, was that C1 times V1 equals C2 times V2. And so rather than X and Y, we have C and V here, but you can see it's that exact same setup. So we know that the concentration of a solution and again, this is given that the amount of serum is not changed. Is inversely related to the volume. So by volume here, it's implied that the volume is the amount of sterile water or NS that has been added to that solution. The more we add, the lower the concentration gets. Let's take a look at an example here. A 120 milliliter solution has a concentration of 15%. At what volume would the concentration be reduced to 10%? So let's say we don't remember this formula up here, C1V1 equals C2V2. But we do know that the two quantities are inversely related. The more water you add, the lower the concentration is. So we know that the concentration is a constant divided by the volume. Now we have that known condition, 120 milliliters and 15%. So we put 15 in for the concentration, equals K over 120. So we're going to get a really ugly number here. We're going to multiply by the 120. 15% times 120. I believe that's 1,800. I'm going to double check that. It is 1,800. So we know the constant's 1,800. So we can redefine this formula here. Instead of C equals a constant divided by V, we know that constant's 1800. So C equals 1800 divided by V. And now we want to know at what volume will that be reduced to a concentration of 10%. So I put 10 in for C. Get back here. And I'm going to solve for V. So here, because I chose to do C equals K over V, I could have done V equals K over C. Remember, inverse relation, doesn't matter what order I put the variables in. But because I did it this way, the variable I'm solving for is on the bottom of a fraction. And that's always a little bit inconvenient to work with. But the way to make it simpler is to do this. We put the 10 over 1 to make the left side a fraction as well. And now this is a proportion. So we can solve by cross multiplying and dividing. So the two numbers that are diagonal with each other are the 1 and the 1800. We multiply 1 times 1800 to get 1800. The number that's diagonal with our missing number is the 10, so we divide by the 10. So our volume becomes 180. And of course, that was in milliliters, so this is 180 milliliters. So if we increase that volume to 180 milliliters, the concentration will be 10%. It's currently 120 milliliters, so we know we have to add 60 milliliters of normal saline, of NS. So there, if we didn't remember that formula for the change of the concentration, we could simply use the fact that we knew it was inversely related to derive the result without having to ever know the formula. Look at another one, the gas law I had talked about, the ideal gas law. Now, I am going to qualify this as for a set temperature. If you're allowed to change the temperature, everything else here changes as well. So if we keep the temperature the same, the volume of a gas, I'd say the volume occupied of a gas, is inversely related to the pressure. So what does that mean? That means if I want to take a gas and squeeze it into a smaller volume, it's going to be at a higher pressure. If you ever worked with a gas grill, those LP tanks, that is extremely high pressure propane. In fact, gaseous propane is compressed until it turns into a liquid, and then it's put into that tank. That tank keeps it compressed in liquid state so that you can have quite a large volume of propane in there. That little 5-gallon propane cylinder that you use on your grill, it's in liquid form. When it's full of liquid propane, that 5 gallons of liquid propane is under enough pressure that it is equivalent to 300 gallons of gaseous propane at standard atmospheric pressure. So if you were to release that, that would be 300 gallons worth of gaseous propane coming out of that tank. So let's take a look here at an example here. So at pressure of 12 psi, pounds per square inch, a gas occupies 150 cubic inches. Find the pressure required to reduce the volume to 60 cubic inches. So again, we knew that this is an inverse relationship. So the volume is equal to a constant over the pressure, inversely related to the pressure. And we have this initial condition. At 12 psi, we occupy 150 cubic inches. So 150 cubic inches is the volume. We put that in here for V. Equals K over 12 would be the pressure. Then we're going to multiply by 12. Divide, multiply. Get K by itself. So 150 times 12 is 1800 equals K. So we know that our volume equals 1800 divided by the pressure. And now we're asked to apply it to a new situation. Find the pressure if the volume needs to be decreased to 60 cubic inches. So we put 60 in for V. We're going to solve for P. Well, once again, the variable we're solving for is on the bottom of a fraction. So I'm going to put the 60 over 1 to make this a proportion, and I'm going to cross multiply and divide. 1 times 1800 is 1800, and I divide by the 60. Gives us 30. So the pressure has to be increased to 30 psi to reduce the volume of that gas down to 60 cubic inches. Another inverse related problem. Back to light intensity. The intensity of light on a surface is inversely related to the square of the distance from the source. So what's this telling us? Intensity, I, is inversely related. So that's K divided by the square of the distance from the source. So that's D for distance squared. If at 30 inches from the source, the intensity, the surface intensity, we're just going to say the intensity here to save time, is 9 lumens per square inch. Find the intensity . 40 inches from the source. So we have that known condition here. 30 inches from the source, the intensity is 9 lumens. So I put 9 in for I equals constant K over, our distance is 30, but remember it's D squared, so it's 30 squared. Now I have an intermediate step here before I solve. I have to square the 30. That'll be 900. Now I multiply by 900. Oops, not divide, multiply. Get K by itself. So I get 8100 equals my constant. So the formula here, the intensity I equals 8,100 over the distance squared. Now we put in our new situation, the 40 inches. I equals 8,100 for 40 squared. Now I'm just going to punch this in the calculator. 8,100 divided by 40 squared should give us 5.0625 lumens per square inch. So just over 5 lumens per square inch. So just going 10 inches further away reduces it from 9 lumens to 5 lumens. Almost cuts it in half. Okay, so the homework based on this variation stuff is page 240 through 241. 1 through 21, the odds. I want to take just a second here to cover some things that we didn't quite get to on Monday. And that's parallel lines and perpendicular lines. And then what I'm looking at is in terms of the graph and the equation. Well, we saw earlier that two lines, they have the same angle across the graph, they're parallel. That means they have the same slope. Perpendicular lines are a little more complex. We can find two things though. If two lines are perpendicular, first thing we know is if one of them has a positive slope, the other one has a negative slope. So that's what we call opposites. One positive, one negative. And what happens if we draw in the rise and run triangles here, when we put in that perpendicular, the rise will become the run. And the run become the rise. So it flips it over, which is called a reciprocal. Opposite reciprocal slopes for perpendicular lines. So if I ask you, find the equation of a line perpendicular to y equals negative 2/3 x minus 5, and through the point for 5. Well, all we need from this equation here is the slope. That slope is negative 2/3. The perpendicular slope with the opposite reciprocal. So a positive 3/2. So the negative became a positive, that's the opposite part. Then we flip the 3 and the 2 to make it, instead of 2/3, it's 3/2. So that is our perpendicular slope. So our new equation starts out y equals 3/2 x. And then we have to find that y-intercept. And just like we did last class, we put the 5 in for y, and the 4 in for x, and we can calculate b. 3/2 times 4 equals 6. Subtracting 6, b is negative 1. So that equation becomes y equals 3/2 x minus 1. Okay, so that is our time. We'll look at parallel and perpendicular lines more on Friday again. There's a couple of Unit 3 tests that I don't have back in, so if you're still working on those, get those finished up as soon as you can. I would like to take some class time to answer any questions on any of the problems that you'd like me to go over on that test once I get them all graded. So I hope you do corrections in class time on those if we get a chance. But with that, you guys have a great day. Hopefully we'll see you all on Friday.